So in this section we're talking about L'Hopital's rule, and so I thought I'd start by talking about the spelling of L'Hopital. Maybe talk about the mathematician himself. So this is a picture of the Marquis de L'Hopital. Notice the time frame we're talking about is 1660 to 1700, so about the same time frame as Sir Isaac. And Leibniz was also right in there at the same time. So just to mention, um, so L'Hopital was famous mostly for this book that he published that's kind of put a lot of the ideas of calculus together. And so L'Hopital, he didn't invent the rule that we're talking about, but the rule does appear in his book. And so, by the way, you'll notice here that the spelling of L'Hopital looks like La Hospital, and that's how he spelled it himself, and that is how our book author also spells it. But you'll notice that in this great biography, it's spelled differently with this O with a, I guess that's called a circumflex. We could say O hat if you'd like. And by the way, this web page is a pretty good one for looking up biographies of mathematicians. So you see here if you do a search on Mac Tutor Mathematics, you'll see this. I'm not sure why they call it Mac Tutor. This is put out by the University of St. Andrews, and they have lots and lots of biographies of different mathematicians. And so if you go to their homepage, you'll also see mathematicians of the day, and that's kind of fun to look at. You'll also see who was born on this day and who died on this day, the mathematicians. So you can check that out. All right, so you can see which mathematician shares your birthday. Okay, so I just wanted to mention, the spelling of L'Hopital, and then so far we've got two different versions, and actually, if you go to the internet, you'll see lots of different versions. So I just wanted to mention one note here on Wikipedia. It says that in the 17th and 18th century, it was commonly spelled as L'Hopital, as La Hospital, and then L'Hopital himself spelled his name that way. However, French spellings have been altered, which is kind of an interesting side note. I know several languages go through formal rewrites of how they spell, how they use spelling. Although English, we don't do that, but some other countries do. So it's kind of interesting to see that. The silent S has been removed and replaced with the circumflex. However, if you don't use the circumflex, you can spell it as La Hospital. So you can spell it either way. All right, so I'm going to pause here and we'll set up what we need for L'Hopital's rule and talk about kind of an intuitive version of it before we get started. All right, I'll be right back. Okay, so to get the ball rolling, we're talking about L'Hopital's rule and some of the intuition about it. And suppose we start off with the quotient of functions. The limit as x approaches a of f of x over g of x is equal to 0 over 0. You'll notice first that this is called an indeterminate form. Indeterminate form. And the reason it's called that is because 0 over 0 could mean that the limit does exist. It might mean that the limit does not exist. We just don't know. And so remember way back when we said that we would have to do more work, right, to see if the limit does exist or not. Okay, so this is the case where we can use L'Hopital's rule, and the idea behind L'Hopital's rule is that you can think of f of x and g of x as being approximated by the equation of their tangent lines. Okay, like we did in section 3.10, g of a plus g prime of a times x minus a. Now these are, I shouldn't put equal sign here. I should put approximately equal to. And so if f and g are well-behaved functions, then this approximation gets better and better the closer and closer to a that you get. And also, if we look at our equation here, we can assume that f of a and g of a are going to be 0, and so that actually makes our approximations even easier to write, because if f of a is 0, well, maybe I'll just write it that way. And g of a is 0, we just get f prime divided by g prime, right? Because we'll say this is approximately the limit as x approaches a of f prime of a times x minus a divided by g prime of a times x minus a. And so the x minus a's cancel, right? And you're left with what you want, or the result of L'Hopital's rule. Okay, so before we get too far into that, let's actually, I'm not going to prove L'Hopital's rule, this is just kind of an intuition behind it. So let me go ahead and write up the specific form of L'Hopital's rule, because there are some certain conditions on these functions that we want to be sure are satisfied before we use L'Hopital's rule. Alright, so this is a statement of L'Hopital's rule. It says that if we have f and g, two functions, that are differentiable, and g prime of x is not equal to 0 on an open interval I that contains a point A, except possibly at point A, and further, suppose that my limit of f of x over g of x as x approaches A is 0 over 0, or plus or minus infinity over plus or minus infinity. Okay, remember now the second fraction here, you could have plus infinity over minus infinity, or minus infinity over plus infinity. You just have an infinity over infinity, and then the signs don't really matter. Okay, so if that is true, then we can say that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x divided by g prime of x, provided that the limit on the right exists. And actually, this is a really important statement. So if this limit does not exist, the limit as x approaches a of f prime over g prime, if that limit does not exist, then you want to use a different technique to see if the original limit exists. We'll talk about that in just a second. But alright, so let's just try this and see what happens. So this is our new technique for finding limits. Again, L'Hopital's rule, if you have 0 over 0, or plus or minus infinity over plus or minus infinity, we can use the rule. And in order to use the rule, this says take the limit of the derivatives. Notice that, by the way, that this is not the quotient rule, right? This is derivative divided by derivative. Okay, so let's see how this might work. Example. How about we'll take the limit as x approaches 1 of the natural log of x. Oops, gosh, why did I draw that? My handwriting's not very good there. Divided by x minus 1. Good. Now you'll notice that the numerator goes to natural log of 1, which is 0, and the denominator goes to 1 minus 1, which is also 0. So we do have the 0 divided by 0 form. Okay, so I'll take this out here to simplify our work. And so what our rule says is we can evaluate that limit by taking the derivative divided by the derivative. So the derivative of the top is 1 over x. The derivative of the bottom is 1 minus 1. Oh, sorry. 1. And so now we see that the limit is equal to 1. Good. And so that makes taking a lot of these limits a lot easier, right? If we can use L'Hopital's rule. So let's see, how about another example? By the way, in this example that we just did, right, this technique is almost a requirement, right? Because remember what our old techniques were? We had factor and cancel, we had simplify, we had multiply by a conjugate, and so this is our new technique, L'Hopital's rule. And so how about another example? Whoops. How about the limit as x approaches 1 of x squared minus 1 divided by 3x? Now, if you just use L'Hopital's rule, right, we end up with something like limit as x approaches 1 of 2x divided by 3. And so plugging in x equals 1, we end up with 2/3. However, what do we notice? If you go back to the original problem, should this be 2/3? If I go back to this original problem and just plug in x equals 1, I get 1 minus 1 over 3 times 1, and so I get 0 over 3, which is 0. So which is correct? That's right, we can't use L'Hopital's rule because we did not start with a 0 over 0 form. No 0 over 0 form. Okay, and so the limit, in fact, is 0 in this case. Okay, so be sure and verify that you have the right setup to L'Hopital's rule. So that, again, was either 0 over 0 or plus or minus infinity over plus or minus infinity. Good. How about another one? How about let's do an infinite one. How about the limit as x goes to infinity of another natural log here over the square root of x? Alright, so in this case we can check real quick. Natural log goes to infinity as x goes to infinity, so the numerator goes to infinity. Denominator also goes to infinity, so we do have an infinity over infinity form. And so now we can use L'Hopital. Sometimes I'll indicate L'Hopital with an L and a circle around it, just so I remember that I'm using L'Hopital's rule here. And so the top, the derivative of natural log was 1 over x. The bottom is 1/2 times x to the minus 1/2. And so before you go any further, be sure and use some algebra here to simplify that. And so in this case, right, I'm not putting an L here because this is just an algebra issue here. So that's 1 over x, and then I'm going to, let's see, this denominator is 1 over 2 square roots of x. Right, so if I invert and multiply, oops, sorry about that. Good. And so then, what do I get here? It looks like I get the limit as x goes to infinity of 2 over the square root of x. Can I use L'Hopital's rule again? I cannot, right? Because I don't have infinity over infinity anymore. I have 2 divided by infinity, and we know that that is going to 0. Good, because that's the numerator is fixed, but the denominator is getting larger and larger and larger. Good. And so we've seen a couple of examples of L'Hopital's rule. In the next video, we'll continue a couple of examples, and we'll take a look at some examples where we do have to be a little bit careful about some of the conditions of L'Hopital.